Hello everybody, welcome to another lesson by me, Miss Pythagoras. In this lesson, I will explain how to find the stationary points of a cubic function. Now this is the first lesson of 6 on sketching a cubic function. Remember, you can also visit my website onlinemaths.co.za and find all the chapters in the grade 11 and 12 syllabi. The link is in the comments below. And remember, if you haven't subscribed yet, please do that now in order to automatically receive all my new lessons. Back to the maths. Now, in order for us to sketch the cubic function, there are two very important points, and they are the stationary points, or sometimes they are referred to as the turning points, and then the last point, the point of inflection. Let's have a look at those. To start with, the general equation for the cubic function is y is equal to ax cubed plus bx squared plus cx plus d. Now, first of all, the shape of the function. When a is greater than 0 or positive, then this is the shape. We say it's an ascending function. When a is smaller than 0 or negative, this is the shape and we say it's a descending function. The next thing that you need to know is something that we call the turning points, or we refer to them as the stationary points. Now, when your a is positive, greater than 0, this is the shape of your graph. Then you will see that there at the turning point or the stationary point, there's your tangent, and the gradient of the tangent at that point is exactly 0. And can you remember from the first course where you find the gradient when you find the derivative? So now we will find the derivative equal to 0 when we find the turning point or the stationary point. And this is the reason why we do the cubic function in the calculus chapter, is because of stationary points. So to find the stationary point, you find the derivative equal to 0. Why? Because the derivative means the gradient of the tangent, and at the turning point, the gradient of the tangent is exactly 0. That point is also referred to as the local maximum. Again, there's another turning point there, or stationary point. There's your gradient to the function, and the gradient there is exactly 0. Therefore, to find the turning point or the stationary point, we will find the derivative equals 0. And that point is referred to as the local minimum. Now, your turning point or stationary points when a's value is smaller than 0, in other words, when a is negative, this will be the shape of your graph. Again, there's your turning point or your stationary point. The gradient of the tangent is equal to 0. Therefore, to find the stationary point, you will find the first derivative equals 0. And that point is also called the local minimum. The other stationary point or turning point is that point. The gradient of the tangent is exactly 0 there. Therefore, we will find the derivative equal to 0 when we work out the stationary points. And that point is called the local maximum. Now let me show you how to work out the coordinates of the turning point. The question here says, give the coordinates of the turning points of the function f of x is equal to x cubed plus 3x squared. And then there is your function. I sketched it for you. Remember, you can't sketch it yet, but I gave it to you just to show you where the turning points are. Now, to work out the turning point, you need the function, and then you're going to work out the first derivative, and you're going to equate to 0. So the first derivative there will be 3x squared plus 6x equals 0. And remember, we will factorize now to solve x. So we will take out 3x as a common factor, and we're left with x plus 2 is equal to 0. Therefore, 3x is 0 or x plus 2 is 0, x is 0 or x is negative 2. Then every x has an original y value. That means that now you will substitute x is 0 and x is negative 2 into the original equation. Therefore, there's your original equation. In x's place, everywhere where you see x, you will substitute 0 and you end with the point 0, 0. Now have a look at the sketch. There at the point 0, 0, you will find your first turning point or your first stationary point, and that is also the local minimum. Then back to x is equal to minus 2. We will substitute that one into the original equation. Everywhere where you see x, you substitute negative 2. Then negative 2 cubed is negative 8. And negative 2 squared is plus 4 times 3 is 12. Negative 8 plus 12 is 4. So your other turning point is the point minus 2 and 4. And if you go to the sketch, you will see the stationary point there, the point minus 2 and 4, and that point is also referred to as the local maximum. Now there's something else I want to discuss with you, and that is called the point of inflection. Now this is the point on the cubic function where the concavity changes. So when I give you the equation, the function there, that point over there, the purple point, that is the point of inflection, the point where the concavity changes. The cubic function can change from being concave down to concave up and vice versa. Now, if you look at the graph there, you will see there's the purple line, that's the middle. And then on the to the left of that line, can you see that your graph is concave down? It looks as if your graph is crying. And then to the right of that point of inflection, there your graph is concave up. Can you see your graph is smiling? We find the x-coordinate by the second derivative. So we will find the second derivative. Now what is that? The second derivative is just you find the first derivative, and then the answer you got, you find the derivative again. So it's the derivative of the derivative, and we will equate to 0. So there you will see the second derivative equal to 0 will give you the point of inflection. And then the point of inflection is always halfway between the two turning points. Let me show you an example where we will work out the point of inflection. So the question here says, give the coordinates of the point of inflection of the function f of x is equal to x to the 3 plus 3x squared. Now this is the one where we worked out the turning points for, and you will find them there. Now let's zoom in on the point of inflection. So first of all, there's your function. To find the point of inflection, we will find the second derivative and equate to 0. Now, there's your first derivative, 3x squared plus 6x. Your second derivative will be 6x plus 6. And we equate it to 0, the second derivative, and we solve x. 6x is equal to minus 6, x is equal to negative 1. And then every x has an original y value. Therefore, you will substitute x is equal to minus 1 into the original equation, and then you end with 2. So when you go to your sketch, you will see there that the point of inflection is indeed the point -1 and 2. There it flew in and there. That's the point of inflection, halfway between the two stationary points. Now, there are some cubic functions which can have a stationary point that is also a point of inflection. Now, let's quickly zoom in on the graph where a is positive. There you find this one. Then, the equation for this graph is f of x is equal to x cubed minus 1. When you find the first derivative, it is 3x squared, and when you find the second derivative, the answer is 6x. And when you equate it to 0 and you solve x, you get x is equal to 0. Then, when you substitute 0 into the original equation, you find the corresponding y coordinate is -1. So therefore, the point of inflection here is at the point 0 and -1. And that is the stationary point and the point of inflection. The first derivative equals 0 there, and the second derivative equals 0. And then to the left of the point of inflection, you can see that your graph is concave down, and there at the point of inflection, the concavity changes, and suddenly to the right of the point of inflection, your graph is concave up. Now you know how to find the stationary points and the point of inflection of a cubic function. The next lesson is how to sketch a cubic function. Click on the video in the right-hand corner to take you straight to that lesson. This is Miss Pythagoras signing off. Till next time.